Okay, so we're back. So this is going to be somewhat short, but I think it'll be pretty straightforward and pretty basic. So what we did just now is we computed a comprehensive suite of distribution factors, and we basically arrived, when it was all said and done, at two numbers for moment and shear, a distribution factor of 0.86 for moment and a distribution factor of 0.952 for shear. Okay? Now, where do we use those? Okay? If you recall, I showed you all this program a little while ago, this LEAP consist. Let me check something real quick. I think the units might have gone back to SI. Oh, no, they did. Same metric. Okay. All right. So if you recall, I showed you this program, LEAP consist, and what this program is a way of very rapidly and quickly doing structural analysis for bridges. It'll do all the influence line and moving load stuff. So it's pretty basic. All you do is this. Once you go through and define your beam, which we had done this a while back, we went and it was a two-span bridge, 90 foot long, threw in each of our moments of inertia. The only thing I would point out is I'm doing, in this file, I'm doing a short-term composite analysis. So if you look at my moments of inertia, they're not the steel-only moments of inertia. They're a little higher. I'm using the short-term composite moments of inertia. So if you go, like for this positive bending region, I'm using what, 48,795. If you go to my section properties, go to positive bending, for an exterior girder, moment of inertia, 48,795. So you see where that's coming from. So I'll show you what I've got here in this table. So I go to loads, and I might just delete all these out just to show you how this works, because it's really simple. I'm going to delete all these out. Okay. So once I define the model, it's really this simple. I go over here on the right, and I go through my basic loads and figure out which ones I want to do. So if I want to do an analysis of the design truck or the design lane or the design tandem, let's take the truck. I take the truck, I drag it over, I right-click, I hit View Results, and that's it. And it's pretty basic. It went through, it divvied up the structure into 10th points. It drew an influence line for every 10th point. It then went through and, determined the maximum and minimum truck placements, for maximum and minimum moments, maximum and minimum shears, and did that across the board. All right? That's literally all this is. In fact, if you want, you can, let's see, I never really do this, but you can go to influence lines and literally hit play, and you can watch the influence line sort of go down the structure. So far, so good? So I go to loads, view results. I can look at a report, and it's generating the report. If I zoom in, you can see all my moment envelopes. So if I look at a given location, let's say, 36 feet over from the edge, I have a maximum positive moment, a maximum negative moment, a maximum positive shear, a maximum negative shear, right? So all I did is I took those values and I dumped them into Excel, and it looks something about like this, okay? So that's literally all I did. I just prettied it up for our use. So let's explain what's going on with this table. So I've got unfactored and undistributed moments, and if you look here on the tabs, I've got moments and I've got shears, okay? Now the shear table's organized a little differently. There's actually two values at x equals 90 feet because I wanted to represent that jump in the shear diagram where you get the vertical reaction at the support. Okay. Now where did I get these values? I literally just generated a bunch of reports out of LEAP consist and just copied and pasted the numbers into the table. It's really it. And how did it do this? Influence line analysis, truck placement, load times influence line value. That's just kept going through that. Okay, so let's sort of discern and make sure we understand what's going on. So I've got a bunch of dead load moments here. So it's just dead load moment, dead load moment, dead load moment. And then I have live load envelope. Okay, so for a given point, let's say at x equals 30 feet or 36 feet, I have a maximum possible positive bending moment, a maximum possible negative bending moment. And remember, from an influence line analysis, at a given point, we can generate positive and negative bending. So it's all about the extreme effects. Make sense? Everybody good? Okay. Now I've got all these given components. I've got the truck, the lane, the tandem. Now the double truck and the double tandem, what's going on there? I've only got values that are negative. Why? Negative bending. Remember, the double truck and the double tandem, they were used for negative bending investigations. Remember that? Okay. And then I've got my fatigue truck over here. We'll probably deal with the fatigue truck later on when we actually get to fatigue. Okay. So there's moments, and then there's shears. Okay. So let's figure out, first off, how we actually combine these. Okay. So does everybody at least have a general understanding of how you would generate these numbers? You know, the numbers for the truck, for the lane, for the tandem. Everybody okay with that? Influence lines and all that. You're giving me a look. What's up? Okay. All right. Okay. First thing we have to do is we have to combine these appropriately. Now, how do we combine these? I told you all a while back that there was a particular slide that I wanted you all to put a star on in your notes. I think it was this last slide right here. Y'all remember that? Okay. So, for strength and service limit states, we have 4 cases, right? Remember these? Okay, so let me show you what I got going on over here. In this table, I've got, it's funny how I put 4 cases. I'm clever like that, aren't I? Sound good? All right, so let's do each one of these, all right? So the first case, okay, it's 100% of what? Y'all have your notes out? Goodness gracious. Making you all go through notes? 8 o'clock at night? I'm horrible, aren't I? Now, keep in mind, a lot of software programs will just do this for you, but I want you to understand what it's doing and why it's doing it. So what's our first case? What we got? All right, there we go. Okay. So watch what I'm going to do. I'm going to say equals 1.33 times, I'm going to scroll over here, 1.33 times the truck plus the lane. See how I did that? So I took that first value and I said 1.33 times the truck plus the lane. I'm going to hit enter. So that gives me a value. Obviously it's 0, but I'm going to take this value and I'm going to copy and paste it all through here, and we'll just say, just paste the formulas. Okay. So if you notice, for each 10th point, in each cell, it's taking 1.33 times the truck plus the lane. Make sense? Now what's the next one? If it's 1.33 times the truck for the first one, it's 1.33 times what for the second one? Tandem. All right, so equals 1.33 times, scroll over, the tandem plus the lane. And then copy that value, or paste it throughout, and just paste the formulas. All right. So see what's going on? I got 1.33 times the truck plus the lane and 1.33 times the tandem plus the lane. Now, I've got the third and fourth case, which is only for bending, and that's 90% of what? 1.33 times the double truck plus the lane. Y'all see that? So I'm going to say equals, we'll say, and you can actually say 90% times, at least I think you can, times double truck plus the lane. Yep, there you go. Or if you want, you can say 0.9. Now you could say, well, I thought that was only for negative bending. Well, look at your double truck values. There's only negative bending values there. And then we've got equals 1.33 times the double tandem plus the lane. Oh. All right. Everybody good? So take that. Paste the formulas. Okay. So the next thing I need to determine is which one of these cases govern. So if I'm the engineer, I want to pick the worst case scenario. So look, I've got a series of positive values and a series of negative values. Let's look at the positive values first. What would be the worst case scenario from this column, this column, this column, and this column? Be the maximum, right? Sound good? So I'm going to say equals the max of, what do I have? That, and that, right? So that'll give me the largest positive bending moment that I can get from live load, or from my live loads. Sound good? Everybody good? All right. And then we'll drag that down. Now, okay, that's for the positive values. How would I calculate it for the minimum, or for the negative ones? I just told you. And the minimum. Well, we would need the minimums, right? Yeah. I sort of let that one slip. Whoops. So we would say equals the minimum of case 1, negative, case 2, case 3, case 4. So this is literally the worst case scenario. Sound good? Drag that down. Okay. So what's going on in this series of columns right here under governing is this is still what we would get out of a computer analysis, you know, a line girder analysis, drawing 20 kips on a beam and drawing a shear and moment diagram, what you all learned in Structures 1. That's all that's going on here. Now there's a lot of numbers, but that's basically it. We then need to take those moments and turn them into real life moments. Okay? And that means distributing them, which means using a distribution factor, figuring out how much of this moment goes to a particular girder. So we then go to our distribution factors and say, what was the worst case distribution factor for moment? And what was that? For moment. What's that? Yeah, no, I mean what we calculated. When we went through and did all this massive set of calcs, what did we get for moment? What was the worst case? It was this 0.86, right? So what I'm going to do is I'm going to say 0.86, 0.86, and I'm going to copy that number all throughout. All right, see what I'm doing there? All right, now if we had gotten a different value for negative bending, I would put a different distribution factor in right here. Why those cells? Because those are the cells around the negative bending. Does that make sense? So I would have, you know, 0.86, 0.86, 0.6, and then maybe 0.9, you know, or whatever. Make sense? All right. I then need to distribute this governing case right here to obtain the actual ones I can factor. So how am I going to do that? I'm going to take this column, multiply it by the distribution factor, and I'm going to take this column times the distribution factor. See what I'm doing? Sound good? And then, whoop. So if you want these moments right here, those are the actual live load moments that we can factor. In other words, this is kind of the whole 1.2 times the dead plus 1.6 times the live that you might remember from building design. These are the loads that I can begin to start factoring because I've taken each of those components, I've combined them according to the spec, and then I've distributed them to this bridge according to the distribution factors I computed earlier. Make sense? All right. All right. So let me sort of go over here. So I created another little table here for my load combos. So let me go ahead and fill it in. So my dead load moments, I'm just going to be lazy and copy and paste that. I'm going to copy and paste this right there. So these are my dead load moments. My live load moments come from right here. Oh. Okay. So here are my dead load moments. Here are my live load moments, right? So now I've got to factor them. Do I do 1.2 times the dead plus 1.6 times the live? No. What do I do? I'm going to take it way back when. Let's go to this handout. Remember this? This was I think the third handout I gave you all. It was the limit states design, where we went through and talked about the reliability. Well, at the very end, we went and discussed the limit states in the spec. Okay? Remember how we did this? We went down and we started eliminating the stuff that didn't really matter for steel bridges and arrived only at the strength limit states that we cared about, and then or the strength and service limit states and whatnot that we cared about, and then narrowed it down when we got to this. Remember that? Been a while, right? All right. Well, what I'm going to do is I'm going to use this to determine factored moments, factored shears. How am I going to do that? Let's start off with strength 1. 1.25 times the DC components plus 1.5 times the DW components plus 1.75 times all my live load components. Live load plus impact. Remember that impact? That was that 1.33 we kept using. That was that dynamic load allowance factor. So that would be strength 1. If we wanted to do strength 3, strength 4, strength 5, similar instance. Sound good? Okay, so let's go through and do that. So here's my load combinations. All right, so strength 1. So what do? I say 1.25 times DC. So I've actually got 2 DC components. So I'm going to say DC1 plus DC2 plus 1.5 times DW plus 1.75 times my live load. And since I've got an envelope, I've got positives and negatives. I got to do 1, let's see, come on, 1 here, and then I've got to do the same thing. DC1 plus DC2 plus 1.5 times DW plus 1.75 times, oh, come on, touchy with me. Oh, there we go. All right, sound good? Take that, drag it down. So these moments are my factored moments. This is my, MU. Remember, the factored moments that we're dealing with. Let me bold this for a second. Actually, let me bold that. In fact, I'm even going to do something different. I'm going to plot it. Okay. So let me go over here a little bit, and I'm going to insert plot. Let's do a scatter plot. Oh, I don't want the whole thing. So let's add some data. So I right-click, select data, and I'm going to add 2 data series. So we're plotting x, y data. So here's my x coordinates, here's my y coordinates. So let's see. All right, so the x coordinates, here's along the span. Y coordinates, let's do the positive moments. Okay. X coordinates. Right. I feel like I have an error in here somewhere. Did I? Oh, that's supposed to be a plus. No wonder. There we go. All right. Drag that up a little bit. Okay. So what we're looking at here, this kind of looks like a moment diagram, doesn't it? But it's not. Okay, it's not a moment diagram, it's a moment envelope. Okay? Let me adjust my y or my x-axis a little bit. So format axis. Let's see. Let's go from 0 to 180. And let's put that labels. Let's drop them down a little bit. Okay. So here's my plot, and now this looks a little bit more like what I'm after. So on the x-axis, I'm going from 0 to 180 feet. Okay. In other words, the length of the beam. Now, if I go back to this, go back to the very end. Remember, this is the beam I'm after, right? Two 90-foot spans, right? I propose to you that for this beam, this is the design moment envelope according to strength 1, okay? So what I would then do is the next step, I know it's taken 4 or 5 weeks to do one step of this problem, but the second step would be to then say, all right, here is this beam, what is its moment capacity? Is it strong enough to resist these moments? So, for instance, if I'm looking right here, I have a range of moments anywhere from, around, 500-foot kips to, like 4,000-foot kips. So obviously the 4,000 is what governs. I then go through and compute my capacity and see if it's greater than that. If it isn't, that means I've got to resize that beam. I've got to change the flange size, change the web depth, or what have you. Make sense? All right. Any questions? All right. So this is your strength 1 moment envelope. This is a load combination. Another load combination is service 2. And how do we calculate service 2? Those are those elastic and permanent deformation checks we're going to do later. It's very similar. Mostly, since it's a service limit state, most of our load factors are 1. We do up the live load a little bit for that assurance. So let me go back here. So maybe I should title this, I should say, strength 1 moment envelope. And if I want to be technical, I can say, all right, let's add some axis titles. Say, this is the distance across the beam, and it's in feet. And this is my moment, and it's in foot kips. Something like that. Okay. Sound good? All right. Now for service 2, it's very similar. It's just a different load combo. Because for service 2, I just say add up all the dead loads and take the live load and multiply it by 1.3. 1.3 times that. There we go. And then for service 2, for the negative, same thing. That plus that plus that plus, I did minuses. Plus. Now looking at this keyboard, it's like, with this light, it's really, I can barely read it. Fill out format. Okay. So because the load combo is different, obviously the moments are a little lower, but it's because we're doing a different type of check when we do service 2, and we'll look at that later. Sound good? All right. We can do something very similar with shear. The shears are actually, there's a lot less going on. See, if you go to the shear tab, if I go to the distribution, there's no case 3 and case 4. Why is there no case 3 and case 4? Remember, case 3 and case 4 were for negative bending regions, right? We're not talking about bending here. We're talking about shear. We only have to do case 1 and case 2. So I can fill this in pretty quickly. I can say, all right, for case 1 equals 1.33 times the truck plus the lane. Notice how there isn't even a double truck or double tandem at all, okay? The way these software programs work, they don't even report the shears. You don't need them. So 1.33 times the truck plus the lane, and then I can go ahead and do this one, equals 1.33 times the tandem plus the lane. Drag that over. Drag that over. And then, all right, so went ahead and computed that. Got to compute my governing. So for the positives, I'm looking for the maximum shears. And for the negatives, looking for the minimum. And again, if I'm going kind of fast on the Excel, you know, you can always go back to the video and replay it over and over again. All right. So far, so good? All right. Now, distribution factor. Let's see if y'all remember. What was the worst case distribution factor for shear? Hey, can you go through your notes again? 1.952. There we go. So 0.952. All right. And then for live loads, I'd have to distribute them. So take the governing case times the distribution factor. Governing case times the distribution factor. Right? Now we got to do a load combination. So I'm going to go ahead and just copy and paste these shears over because I'm lazy, don't want to do the formula. So copy and paste those. The live loads, those equal that. And there you go. All right. So the last thing left to do is to do a load combo, and I'm only going to do strength 1. It's the only shears I need right now. You don't need to do a service check for shears, and we'll learn that later. So same load combo equals 1.25 times the DC loads, excuse me, plus 1.5 times, or I don't need the parentheses, the DW, plus the 1.75 times the positive shears. Come on, there we go. And then I can actually just copy and paste this formula. I'm using Control C and Control V to do that quickly. And then just sort of, come on, that's being touchy. Just copy and paste that over. So these are my factored shears. And if you want, you can plot that out, see what it looks like. So insert plot. So right click, we'll select data. Now let's add some series. So the first one, there's my x coordinates. And here's my y coordinates. Second one, here's my x coordinates. Here's my y coordinates. So there's your shear diagram. Let me change my axis up a little bit. So I'll right click, format that axis, make it go from 0 to 180. Drop those labels down so I can actually read what's going on. And there we go. So here is your factored shear envelope. So we'll use this later on to determine whether or not the web is sufficient in resisting the shear, and if not, we will use it to space out stiffeners. Okay? So we'll determine how far apart do we need to space stiffeners. Okay? Sound good? So yeah, so for a given point, let's say at the abutments, we have to resist a shear anywhere between 250 some kips and about 54 kips. Obviously, we're going to use the 256 for purposes of design. Make sense? This is what a software package does to compute moments and shears for purposes of design. We're then going to take these moments and see whether or not the girders are appropriate or appropriately sized to resist them. Sound good? All right. This took a little bit longer than I thought, but I'm glad I took my time and went through it slowly. I gave you all some handouts today, but you know what? Let's just not look at them. We'll look at them next week. Because next week what we're going to do is we're going to stop talking about these loads so much and start getting into resistance. How strong is the girder? Is it strong enough to resist these loads? Just like with section properties, we are going to sort of take a step back and do some fundamental calculations before we get into the behavior, so we'll take our time with that. But this was, I know, a grueling set of calcs, so we'll try and do our best to calm down a little bit on it. All right, sound good? All right, that's all I got for you all. You all have hung in there quite well with this. I know it's been a long set of calcs. We'll see you all next week.